Hello everybody. So we are going to start on our last unit of AP Biology. In this case, it's all about ecology. So we're going to start off with populations and how ecology is affected there, and then kind of move on to interactions and other things. So things you must know. This is kind of pulling it back from freshman year, but there are a couple of equations in this particular section where we're going to talk about how populations grow. And there is exponential growth, and there is logistic growth, or a log curve, and there are factors that can affect how that population grows. So, what is a population? Again, basically, it's a group of individuals of a single species living in the same general area. And we had talked about this in evolution also, but for our purposes here, we're going to talk about, a group of a single particular species living in a certain area. And this brings about two other vocab words, density and dispersion. Density is just a measure of how many individuals there are in a certain unit area. So the more individuals in an area, the more dense it is. The less individuals, the less dense. Dispersion has to do with the pattern of spacing. So if there is, equal dispersion, then the area with which you're talking about is equally covered. Versus if you looked at a map of a state, for example, there's not necessarily equal dispersion because the big city areas have a way higher density of people than the more rural areas. So that would mean an uneven dispersion. Okay, so ways in which you can actually count this stuff. You could count every individual, which in a small area, that's not a bad thing. But with larger populations or larger areas, it becomes a little bit unmanageable. So other ways in which we do this are random sampling. So you might measure out a small unit of space and count what's in there, and then just kind of multiply it by the total amount of space that you have, assuming that your little test area is representative of the entire population. Or we can do mark and recapture. So a lot of times, if it's things like birds, or they do it all the time in the ocean with certain sea animals, you mark one and then you recapture later. And sometimes you end up capturing one you've already captured, and sometimes you don't. So in terms of dispersal, as I mentioned, there are different ways to kind of categorize it. Clumped is the most common. As you can see in A there, I guess those are starfish. They kind of group around specific resources. And oftentimes this is why people do the same thing in metropolitan areas or cities, because that's where a lot of the resources are. But if it has to do with a food or shelter or something, then oftentimes they might clump together. Uniform is like in B with the penguins. That's just equal distribution across the entire population, or across the entire area. And oftentimes it's because the members of a population might not want to play nice with each other, so they kind of want to maximize the distance between them. And then the third is random. Basically, it's just unpredictable spacing. This happens sometimes with plants because of like seed dispersion and things like that. The seeds just, happen to land in a certain spot, and then that's where the plant is growing. And so it's not totally uniform. It's just randomly dispersed. It's not super common in nature, but I would imagine it's more so common with plants. Okay, so now we're going to bring up something called demography. And this is the area of science where you study statistics of populations and how they change over time, because certain populations increase, decrease, and so on. And that's what brings about what we call a life table, which is what's seen on the right here. And it's kind of just a summary. It's kind of morbid, but it basically shows you, this is particularly for ground squirrels in California, but you can see the number of live squirrels based on their age. You can then see how many of them were alive at the start of the year, how many died, and then how many offspring. So it's kind of like looking at overall survivorship. How many were born, how many died, how many are still alive, and then kind of the age breakdown of those organisms that are still alive, which brings about a survivorship curve. And it's kind of a measure of how many organisms or survivors are alive at a specific age group. And so you can kind of see on the bottom, percent maximum lifespan just kind of gives you an idea of how long certain organisms live. And there are 3 different types of survivorship curves that exist. The first one is humans. So mostly humans, we live for a very long time, 70s, 80s years old. There is a very low death rate for humans early in our life. So we have almost, 100% survivorship, and then eventually we go down. And again, this is a log scale, so you can kind of see it's not 100% exactly. 2 is basically a constant death rate over time. So some squirrels in this instance die at birth, and some die at every particular age group, kind of at a uniform rate until there are none left. So there's not, one specific spot where many of them are alive or many of them die. It's uniform, probably due to predation, resources, things like that. Type 3 is an example of oysters, where very, very early on, almost all of them die. Whether it be, again, predation or just general survivorship, a ton of them are dead very, very early on in life, and those that kind of survive past that early curve or dip will survive quite a long time. So depending on the type of organism it is, it has a different survivorship curve. Which leads us to equations. We have measures for how populations can change over time. So for calc friends, we have dn dt, which is a very, very fancy way of saying the change in the population over a certain amount of time. So capital N is representative of the population size, and D is delta, or the change in. So the change in the population over a given period of time. T is time. And so obviously that represents however many people were born minus however many people died, because that would represent kind of the net gain of individuals. And if it is possible that more people died than were born, then that's negative, meaning that the population actually decreased over time. So here's kind of a couple of different countries to show you what those age diagrams might look like in the percentage of populations. So Afghanistan, for example, has a ton of growth. They are in the rapid growth category. You can see males on the left, females on the right, and the percentage of the population. The age is youngest at the bottom to oldest at the top. So you can see there's been a really big boom for Afghanistan, for example, of number of children being born, because almost 9% of the population is in the 0 to 4 age group. And you can see that there's very few older individuals, a ton of younger individuals. The United States has slow growth because we have fewer in the old age group, but we kind of have this somewhat steady group. We had a little bit of a bigger age group around 40 to 50, but you can see we're very kind of slow growing. We do have more individuals coming into the world than we do exiting. And then Italy is an example of no growth. It's kind of skinny at both ends, and it actually went down over time. So that would be an example of what no growth looks like. And just to kind of highlight that feature, in order to get zero population growth, the number of births and the number of deaths has to be roughly equivalent. Okay, so there are 2 ways in which a population can grow. The left is, I guess, ideal for a population, exponential growth. So given a specific time frame and infinite resources, there is exponential growth. You can take the coronavirus, for example. We were in exponential growth for a while. But that's not always something that can actually happen in nature, because at some point you run out of something: resources, shelter, food, whatever it may be. So then enter log growth, and basically it's very similar, except it introduces this idea of a carrying capacity. There becomes a maximum population that can actually be supported by the resources. So it starts as this exponential growth, but then it needs to level off because the habitat or the population, whatever you're looking at, just cannot naturally accommodate anything more. Okay, so exponential growth, as I mentioned, includes ideal conditions. In this case, we're talking, elephants are one example. And because there's unlimited resources, ideal conditions, tons of food, no predators, the population can just grow and grow and grow and grow. And here's the equation for it. The change in population over time, dn dt, is equal to little r, which is a growth rate, times capital N. Please don't think you have to memorize this equation. It will be on the formula sheet, and it is labeled as exponential growth. I'll show you that in a few slides. But it's basically however many, whatever the growth rate particularly is, times the population that you are starting with. And so you just multiply those two numbers together, and then that basically tells you how much the population is changing. So here's an example problem. If you had a certain population of mice growing exponentially, the growth rate of the population, R, is 1.3. The current population is 2,500. How many mice are added to the population each year? Well, to figure that out, you literally just multiply the two numbers together. So 1.3 times 2,500 would give you, in this case, 3,250. Now, that is going to tell you the change in population over a certain time frame. So if this is talking about a growth rate of 1.3 per year, then that tells you how many they would grow per year. It's not the new total, it's how much it actually grew. So if I grew 3,250, that's in addition to the 2,500 that I started with from the previous year. But please understand, exponential population growth is very difficult. It does incorporate carrying capacity, which we're going to call K here. K for carrying capacity. Unlimited resources are rare. So K is kind of represented that maximum stable population. And here's an example of two instances where you can see what that looks like. So on the left, we got a paramecium that's growing, 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 and then at some point it kind of levels off. On the right, we have what's called Daphnia, or a water flea. You can actually see from the dots that its population overshoots the carrying capacity, and then it's just too much to control. And then it kind of actually goes down and then stays at this leveled off point. So the red line is an indicator for where the growth curve, should have been had it not overshot the population. So here's the equation for that. It's still R times N, but now we have this new addition onto the end where we're factoring in carrying capacity, which is something that we didn't do before in exponential growth. So if I'm doing a sample problem, they're still going to give you R. The population, in this case, has a growth rate of 1.1. What is the population growth when N, or the population, is 425? The problem also tells you that K, essentially, or the carrying capacity, is 900. So you just plug those numbers in. And if you were to plug those numbers in this case, you should end up with the number 246.7. Which roughly tells you how many organisms are able to actually be added to the population. So how does it get to be so small? If the growth rate is over 1, well, again, the carrying capacity, because we would have taken 900 minus 425 divided by 900. So this ends up being a fraction. And then when you multiply it, you're going to end up with something smaller than your initial population. So it's a slow and steady growth. It's not going to be a super large number like we saw with exponential growth. Here I just copy and pasted the formulas straight off of the AP formula sheet. So this is what you will have in front of you when you're taking the AP test. So don't think that you have to memorize these formulas. It kind of shows you exactly what exponential growth is. It shows you what log growth is, and it even defines all of the letters on the right. So you don't actually have to memorize these at any point. You just have to be able to use it if you need it. All right. So the last thing here is 2 different types of selection. And there is K selection, which is related to K for carrying capacity. So K selection is for populations that are close to carrying capacity. They live around that K value. So because of that, they oftentimes have high parental care. Thinking about kind of like humans. The parents invest a lot in keeping their young alive. They have low birth numbers just so that they're more able to give paternal care and kind of keep those young alive, which translates to good survival. It is density dependent because they're usually around that carrying capacity. They can only accommodate so many individuals. This is different than R selection. R selection is just exponential growth, have tons and tons and tons of babies with the likelihood of a fraction of them surviving. So cockroaches are an example of this. They have exponential growth. Their parents give them little to no care because they have a ton of babies and don't really survive very well, but the ones that do, it's fine because you had so many. And it's density independent, meaning that they just have as many as they can with, again, the hope that some will survive. Okay, so what actually limits these things? There are density dependent factors, which determines or is determined by population. So density is an important piece to this. So that's when you think about when does the number of individuals matter. In this case, predation, disease, aka coronavirus right now, competition, territoriality, meaning fighting for a certain amount of territory, waste, any other physiological factors. So when the number of individuals actually makes a difference, it's a density dependent factor. Things that are density independent are where population doesn't matter, meaning that it would be of equal importance if you had a ton of individuals or not so many individuals. And this is where things like natural disasters come in. A fire is going to be a fire regardless of how many, individuals are living in a tree, or a flood, or random weather things. So in short, these particular factors can be biotic or abiotic, which is kind of cut off there at the bottom. Biotic means living. So if the specific thing that, they are fighting for or are affected by is living, it's biotic. If it's abiotic, it's not living. So one biotic factor could just be the amount of food that's available. That would be a density dependent biotic factor. Abiotic just might mean the number of, caves available. That's a density dependent factor as well because it's dependent on the population, but it's abiotic, meaning that it's not living. So here's just a graphical picture of what that looks like in terms of density dependent. And now we get into things like population dynamics. Populations fluctuate due to biotic and abiotic factors. if there is a huge flood or a dry season / drought, that can affect population numbers because it will affect food. Predator-prey relationships, which is what this graph is showing, often oscillate back and forth because in this instance, wolves in blue eat moose in red. So if there aren't a lot of moose around, well, then the wolves don't have food to eat. So then their population might go down as a result. And then when the number of wolves go down, well, now they're not eating as many moose. So the moose population can recover a little bit and actually go up. And then as more moose become available, more wolves can eat those moose, then their population goes up. So it brings about this oscillation of predator-prey relationships. And you can kind of see that they're not totally in sync. They're offset a little bit, the peaks are. So whenever the prey peaks, the predator will peak right after because more food is readily available. And that will cause a dip in the prey, which will then cause a dip in the predator. And then that prey can go back up again, and then the moose will go back up as a result. So it's kind of like two offset curves. And you can see that in this case, in 1995, there was a harsh snow. So in that case, that abiotic factor of snow dropped the moose population very heavily. And then that had consequences to the wolf population as a result. Here's another example of the hare and the lynx. Again, you can more clearly see the peaks going back and forth, and the predator always peaks after the prey. So you can see the red peaks are always slightly after the blue peaks. And this is just showing you what a 10-year cycle is. It's also called a boom and bust cycle, meaning that populations will boom up to a point, but then that allows things like the predator to come in, and then it busts the cycle. So they'll start eating all of the hares in this case. And that's the end of this particular PowerPoint.